Hello everyone, welcome to this module on variational autoencoders. Variational autoencoders is a member of the family of latent variable models, specifically the neural latent variable models. So, as we discussed in the previous modules, what is a latent variable model? A latent variable model P theta of x is defined by this particular formulation where the model distribution on the data variable is given as the marginal over the joint distribution of the data variable x and a latent variable z, where z is another random variable that is introduced into the modeling system. This is a k dimensional random variable. Typically, k is much less than that of the data dimension d. So, this is the definition of the latent variable model. Now, the question is, how do we learn the parameters of a latent variable model? We saw a procedure to do that in the last module. The idea is, as usual, to find the parameters theta of the model distribution such that a distributional divergence metric between the true data distribution px and the model distribution p theta is minimized. We also saw that this minimization is equivalent to maximizing what is called as the expected log likelihood, which is also known as the maximum likelihood optimization. We saw that for a lot of cases in the latent variable models, solving the maximum likelihood problem becomes intractable because of the involvement of a latent variable. Therefore, instead of solving the problem of maximum likelihood, we solve an alternative problem using a lower bound on the log likelihood. The lower bound, which we denoted by j theta of q, is given by this particular form, the expectation of log of p theta x and z divided by q of z given x, where q of z given x is a distribution on the latent variable, and while optimizing for the evidence lower bound, we not only find out the parameters of the model theta, but we also find an appropriate distribution q on the latent variable. We saw an example of how to do this in a non-neural model formulation, which was called the Gaussian mixture model, where there is an algorithm to alternatively optimize for theta, the model parameters, and q, which is the posterior latent distribution. So that is what was called as the expectation maximization algorithm. So in this module, we will continue from it and we will take up a question where the objectives are that goal of a neural latent variable model The goal of a neural latent variable model is of three folds. First, we need to learn a latent variable model with unknown p theta of z given x. Please recall that in the expectation maximization algorithm, the optimal q, the variational latent posterior, that would optimize the evidence lower bound was given by p theta of z given x, right? But in the previous module, we saw that not all latent variable models will be defined in such a way that p theta of z given x can be computed. So we need to come up with a generalized algorithm for learning a latent variable model, or rather optimizing the elbow, where we do not know or we cannot rather compute p theta of z given x. So that is one of the goals. The second objective is that since we are talking of generative models here, we need to enable sampling from px. We need to enable sampling or generation from p theta of x given z. So this is that we need to sample from the data distribution. P theta of x given z is the conditional data distribution. We need to do that. The third thing that we desire for these sort of models to have is that we also need to do what is called as the posterior inference, enable posterior latent inference. So what is posterior inference? We need to compute. So this actually means that we need to compute or estimate the posterior of the latent variable given data. So why is this important? This is important because given a data point, we need to know what the corresponding latent variable is, because we can use that latent variable later as a feature for the data vector. Now this becomes an embedding or a feature for the data vector that is of interest. So we need a latent variable model, a neural latent variable model that is capable of doing all these. So we first need to come up with an algorithm that would enable optimizing a latent variable model with p theta of z given x unknown, and we need that model to be capable of both sampling from the conditional data distribution and do a posterior inference over the variational distribution. Q of z given x is called the variational latent posterior. We need to sample from the variational latent posterior because that would enable us feature extraction. Okay. With this as the goal, let us look at an algorithm to solve that. Okay, so algorithm for a neural latent variable model. Okay, so let us start from the definition of the latent variable model. We have p of x to be equal to the integral of p of x and z, this is over z. So this is the definition of the latent variable model, and we also know that what we need to find out is we need to find model parameters theta and an optimal posterior distribution that would maximize the evidence lower bound. Okay, so let us consider the evidence lower bound. Consider j theta of q, which is the objective function that we are trying to maximize. What is this given by? This is given by the expectation of log p theta of x and z divided by q of z given x, and this expectation is with respect to the variational latent posterior. Okay, so let us now simplify this expression a little. So this is expectation of log of the joint distribution between x and z can be written in terms of the conditional of x given z and the marginal of z divided by q of z given x. So this is with respect to q of z given x. Okay, now we use the law of logarithms to break these terms up. So this is expectation of log p theta x given z, and this is with respect to q of z given x, minus expectation of log of q of z given x divided by p theta of z. This is with respect to q of z given x, just using the law of logarithms. This is equal to, the first term remains as it is, if you observe the second term by definition is the Kehl divergence between q of z given x and p theta of z, right? So this is the definition of Kehl divergence. So now what did we do? The objective function that has to be optimized is now written in this particular form, which has two terms. The first term is an expectation of the conditional distribution of data given the latent variable. Second term is a Kerr divergence between q of z given x and p theta of z. Right. So it's a good idea to remember this particular equation, this particular form, because this keeps coming multiple times. So this is the so-called loss function for a variational autoencoder or a VAE. This is also the loss function for a diffusion model and so on. So it's a nice idea to just get your heads around this particular equation. Now, how did we get this? This is simply, we started with the evidence lower bound, which is the lower bound that we constructed over the log likelihood function that we would want to maximize. And we just use the law of logarithms to break it down as these two terms. Okay. Now, the question is, how do we optimize this using neural networks? So, to optimize j theta of q using neural networks. So I've been saying that the latent variable models that we will be looking at are neural latent variable models. So we need that means that we'll be using neural networks to approximate distributions here. So basically the idea is to represent the distributions that we have p theta x given z and q of z given x via neural networks. The basic idea is to, so please look at this equation. We have two distributions here, p theta of x given z and q of z given x. Of course, we have p theta of z here, but typically p theta of z is taken to be a constant. We'll discuss that as we move on. But the two key distributions that we have here are p theta of x given z, which is the conditional data likelihood, okay, and we have q of z given x, which is called the variational latent posterior. So maybe I'll just write the names for it. So p theta of x given z is typically called as the conditional data likelihood. So this is for obvious reasons, right? This is the likelihood. Likelihood is the probability density function. It is the likelihood of the data variable x conditioned on the latent variable. That's why the name, the conditional data likelihood. And this q of z given x, already told us, this is called the variational latent posterior distribution, posterior density or distribution. This is also obvious because what we are looking at is the posterior, because it is z given x. So this is the posterior distribution of the latent variable given the data variable, and it's called the variational distribution because, as I said, this comes from the variational calculus, where when you're optimizing with respect to functions, the branch of calculus that deals with it is called the variational calculus, and the solution is often referred to as the variational distribution, and that's why the name is called the variational latent posterior. So yeah, so the basic idea, coming back to neural latent variable models, the idea is to represent the p theta of z given x given z, which is the conditional data likelihood, and q of z given x, which is the variational latent posterior that comes up in the evidence lower bound using neural networks. Okay. Now the next question is, how does one represent a probability distribution using neural networks? Okay. So how to represent probability distributions or densities, okay, via neural networks. So there are typically two ways to do it. One is the deterministic way. Deterministic representation, where you have already seen one example for it, which is the generator of a GAN. Okay, so if you recall, the generator of a GAN is sampling from p theta of x or x cap, right? In this case, the neural network here is not giving you the distribution that it is modeling, but it is giving you the samples of the distribution that it is modeling, correct? So this neural network is outputs the samples of the distribution that it models. Samples from the distribution that it models, correct? So now I call it the deterministic way because there is nothing, it is not giving you the distribution itself, but it is simply giving you the samples. So once trained, a neural network is always a deterministic function. The randomness is coming from the input of the neural network here, which is now sampled from normal 0 1. So it is simply a push forward function which will transform one random variable to the other random variable. So this neural network is also modeling p theta of x, but it is modeling in such a way that it is giving samples from the distribution and modeling p theta of x in an implicit manner. That means that it is not giving you the distribution itself, but it is giving you the samples from the distribution. Another example of this is a classifier. Okay, so if you look at a classifier, this is the generator of a GAN. This is a GAN generator. So if you look at any classifier, one can think of a classifier as there is some classifier network. A classifier network will take x as an input sample and gives you a sample y given x from the distribution p of y given x. Okay, it will give you a class label y conditioned on the input x. So y given x, the output of this classifier can be seen as a sample from the distribution p of y given x it is supposed to model. Right. So these are the ways where neural networks are used to implicitly model the probability density function, but not they basically give you samples from the distribution, but not the distribution itself. Correct. There is another way to model probability density functions using neural networks, which is a probabilistic way, also called the probabilistic neural networks. Probabilistic representation. So maybe I will call this to deterministic representation. In the probabilistic way of representation, so what do we do is that suppose there is a distribution function that we would like to model using a neural network. Let's take the example of whatever we have right now. Let's say we need to model q of z given x. This is the density function that we would want to model. This neural network takes x as an input, and let's say that the parameters of this neural network are denoted by phi. So this neural network will output the parameters of the density function that it is modeling. Okay, so let's write it down completely. So this outputs the parameters of the distribution that it models. Please note the difference between these two representations. Okay, this will not give you us models, but not the sample from the distribution. No, not the samples from the distribution. Okay, unlike the previous case where the neural network gives you the samples from the distribution that it is modeling, in the probabilistic representation, the neural network will model the distribution by giving the parameters of the distribution that it is modeling, okay, not the samples from the distribution. So this will output the parameters of q of g given x. Okay, this is the probabilistic way of doing it. An example of this is if my z given x, let's say, is a Gaussian distribution, then this neural network will take an x and will output the mean and the variance of this particular distribution. Please note that in any case, a neural network is a deterministic function in the sense that once you try the neural network, during inference, the output of the neural network is not random because it's a deterministic function. However, the way you represent a probability density function or a distribution function using a neural network differs. In the deterministic representation, the neural network is taken to be giving samples from the distribution that it is trying to model. And example for it is the GAN generator. In the probabilistic way or probabilistic representation of density functions, the idea is to get the parameters of the density function that it is modeling given a particular input, but not the samples from it. Okay, so this is the probabilistic way. Now, in a variational autoencoder, the distributions q of z given x and p of x given z are represented using probabilistic neural networks. Are represented using probabilistic neural networks. Okay. While optimizing for the elbow evidence lower bound, we use probabilistic neural networks to represent both the variational posterior and the conditional data likelihood in a VAE. So let us do that. So a VAE or a variational autoencoder looks like this. So we are given data as usual, which are n samples drawn ID from an unknown distribution Px. That is what we would like to model. Okay. Now we have what do we need to optimize is the elbow. So in a VAE, the model is the following. So we have a neural network. Okay, let me write the elbow first. So what do we want to optimize is the evidence lower bound. Let us take this down. This is the objective function, and the model is we have p theta of x is given by the joint distribution, marginal of the joint distribution. This is the model. The model that the VA is trying to learn is a latent variable model. The objective function is given by the elbow. So we need to optimize for the elbow, which is j theta of q. And the way we do it in a VAE is to represent both the variational posterior and the conditional data likelihood using probabilistic neural networks. The following objective function is optimized. Objective is optimized. Okay. Now p theta and q are represented using neural networks, as I said. So q of z given x and p theta of x given z are represented using neural networks, or rather probabilistic neural networks. How do we do this? So we have one neural network to represent the variational posterior. This neural network represents Q of z given x. So the parameters of this neural network is denoted by phi, and this neural network takes x as input because this is a conditional distribution. So what it gives out are the samples of are the parameters of the distribution q phi of z given x. And there is another neural network that represents the conditional data likelihood. So this will take a z, let's call this p theta of x given z, where theta are the parameters of this neural network, and this will give you the parameters of the distribution p theta of x given z. Okay, so the diagrams are not to scale because the dimensions are not showing the not represented using the size of the figure. They are not to scale. Okay, so now this is the setup where this neural network, which represents the latent posterior, is called the encoder network, and the neural network that represents the conditional data likelihood is called the decoder network. Now we will discover why these are called the encoder and decoder network in a while. Okay, this is called, there are two neural networks, one representing the conditional data likelihood called the decoder, and there is another neural network that represents the variational posterior called the encoder network. Okay, now please note that there is no direct connection between the encoder and decoder networks, right? There is no direct connection between the encoder and the decoder networks. Okay, now what do I mean by that? The output of the encoder network is not going as an input to the decoder network in a VAE. Okay, they are not connected that way, they are independent that way, but they are connected via the sampling. We will see that in a while, but there is no direct connection between the encoder and the decoder network. Okay, now what does the encoder network output? Encoder network outputs, as I said, the parameters. Let us push it a little away. It will give you the parameters of q phi, and the decoder network will give us the parameters of p theta x given z. Okay, so please don't confuse phi and theta for the parameters of the distribution. So phi and theta are the weights of these corresponding neural networks. So let us write that. So phi and theta represent or denote the weights of these two neural networks. Of the encoder and decoder respectively. Okay, phi and theta represents the weights of encoder and decoder respectively. So they are not the parameters of the distribution that we are modeling. The parameters of the distribution that we are modeling are the output of these neural networks. Okay, the weights of these neural networks are denoted by phi and theta respectively. Okay, both for the encoder and decoder network. So Yeah, so this gives the parameters of q phi of z given x, and this outputs the parameters of p theta of x given z. So maybe we will make it a little more explicit. Outputs parameters of this, and this outputs, so encoder outputs the parameters of this, and decoder outputs the parameters of p theta of x given z. Okay, and phi and theta, as I said, are not the parameters of these distribution that we are talking about. They are simply the weights of the neural networks. Yeah, but the output of these neural networks are the parameters of this distribution. So we will see how to model them in a while. Okay, so now with this, what are we interested in? We are interested in finding out the parameters phi and theta, okay, the optimal encoder and decoder parameters or decoder weights, such that the objective function that we have, which is the elbow. Now elbow becomes a function of both theta and phi, because we are modeling q as a neural network that has parameters phi. Okay, now elbow has another set of parameters phi, so we need to find the optimal encoder parameters and the optimal decoder parameters such that the lower bound, the evidence lower bound, is maximized. Now the optimization is over theta and phi, and we want to maximize this. Now what is this? We know what the elbow is. Okay. Now to solve this optimization problem, and we have neural networks here, how do we solve an optimization problem using neural networks? Is via the gradient descent, which is the back propagation algorithm. What do we need to do is we have phi t plus 1, okay, to be equal to phi t minus, here we are solving the maximization problem, so we have plus the gradient of the elbow with respect to phi, right? This is how we do one gradient step on the encoder parameters, and for the decoder parameters we do the exact same thing. So we have another learning rate, so it can be anything. So this is the gradient of the same elbow with respect to theta. So here alpha is the gradient step size. So what is this? This is the usual gradient descent. To learn the encoder and the decoder networks.